Hey, welcome back. So in the last video, we saw this kind of surprising idea that reactants don't completely form products. Some of the products actually can break down and reform reactants. And at equilibrium, the rate at which the reactants are forming products is perfectly balanced by the rate at which the products are forming reactants. Now, one of the strangest things I think out of all of this is that it is not completely random. There is actually a constant called the equilibrium constant that tells us what will happen at equilibrium. So for example, let's take a chemical reaction where we've got A of A reacting with, say, B of B, and I'm going to try and do the stoichiometric coefficients in red and the reagents themselves in white, and that's forming C molecules of C and let's say D molecules of D. So this is our very sort of general purpose chemical equation. What we find is at equilibrium, those concentrations actually obey something called an equilibrium constant. We're going to call it K. And it turns out that the equilibrium constant is equal to the concentration of C at equilibrium raised to that stoichiometric coefficient C times by the concentration of D at equilibrium raised to that stoichiometric coefficient D, all divided by A raised to the A times by B raised to the B. So A raised to the A times B raised to the B. So these are the equilibrium concentrations. So they can't be anything. They have to always obey this equation here. And in fact, there's several different equilibrium constants we'll use in this course. So we're going to call this one Kc, and the C down here is going to tell us that we're writing the equilibrium constant in terms of concentrations. So K is always going to be equilibrium constant. Notice that rate constant is also K, but we're going to use uppercase K for equilibrium constant and lowercase k for rate constant. So don't get them confused. We'll see later, actually, there's a relationship between them, which is really awesome. We sometimes refer to this as the law of mass action. And this is a very, very old word for it, a very old phrase for it, rather. A lot of the biologists use this phrase, and it's historical. And if you wonder where it comes from, essentially this top here ends up being equivalent to a mass. So the mass of the products divided by the mass of the reactants essentially is always a ratio. And we don't think about it in masses anymore. We think about it in terms of molar concentrations. But historically, it was first sort of noticed to be the masses at equilibrium were related via an expression like this. So this is a table out of our textbook, which I think illustrates this principle pretty well. So we're going to do a series of experiments. So we're going to start with a particular concentration of hydrogen iodine and hydrogen iodide. And at equilibrium, these are the concentrations that we get, presumably in moles per liter. And again, the equilibrium constant then, it would be the concentration of Hi squared over the concentration of hydrogen times iodine, each to the first power. So here's the expression over here. And notice if we plug in the values we get at equilibrium, we get an equilibrium constant of 50. Now, if we start with a different set of conditions, so if instead of starting with just hydrogen and iodine and no Hi, if we just start with Hi, then at equilibrium we get these concentrations here. And again, if we plug them into the equilibrium constant expression, we get exactly the same value of 50. And again, instead of starting with just reactants or products, there I go again, just left-hand side or just right-hand side, we have one of everything or half a mole per liter of everything. At equilibrium, the concentrations will reach a consistent value that gives us an equilibrium constant of 50 again. So that's pretty awesome, right? So no matter what we do, no matter where we start, right? So there's a couple more rows, we end up with concentrations that ratio to give us a consistent value of, in this case, 50. And equilibrium constants, by the way, are constants, but they're constants at a particular temperature. So if you do all these reactions at 445 degrees C, this ratio of products over reactants will always come to be the same value of 50. Pretty awesome. So here's one for you to try. So pretend you've got an equilibrium between nitrogen and hydrogen on one side and ammonia on the other side. So this is the very famous Haber reaction here. Can you write the equilibrium constant for this? So go ahead and pause the video and try and write the equilibrium constant expression and then unpause it and double check. Okay, so here we go. So the equilibrium constant, Kc, is essentially the concentration of products over reactants. So that's the concentration of ammonia, or NH3, divided by the concentration of the reactants, so nitrogen, times by hydrogen. So always remember it's multiplication, not addition. And that's not quite right. I haven't taken the stoichiometric coefficients into account. So there's a 2 there, so I need to square it here. There's a 3 here, so I need to cube it here. And so at equilibrium, if I measure these concentrations and I square the ammonia concentration and I divide it by nitrogen times the cube of hydrogen, I always get a constant which we call the equilibrium constant. That's pretty powerful stuff.